Welcome you all for the structural analysis course. This is the CDT7. So topic is analysis of non-sway frames by using slow diffraction method of analysis. So these are the lecture outcomes. So we'll directly move to the problem analysis of frame, non-frame as shown in figure by slow diffraction method of analysis. So before going to solve this problem, first we have to identify whether this frame is sway frame or non-sway frame. It's not mentioned anything about the sway. First of all, we have to identify the sway or sway frame or non-sway. So sway is occurs in three ways. First one is the supports are at different level. Then sway is possible, or different type of support. Then is also sway is possible. So A is a support, D is a support. For A and D supports are the same support, the fixed supports. The sway is not possible. That means this is a non-sway frame. They are both are at the same level. Even though supports are same support, if they are at same different level, then also sway is possible. So here for this problem, supports are the same supports and they are same level. So this is a so this is a non-sway frame. And also this first criteria is updated to supports. This is also second one is related to moment of inertia of the columns. Okay. Moment of inertia of first column and moment of inertia of next second column is same. That means this is a non-sway frame. If it is different, then sway is possible. Sway is possible. And third one is digital. So this second one is related to moment of inertia. Third one is related to loading, symmetrical loading. Third one is related to loading. If the loading is symmetrical about the vertical axis, if the loading is symmetrical about vertical axis, then the frame is called a non-sway frame. The loading is symmetrical about, if you see this BC member is subjected to uniform distributed load and this load is symmetrical about the vertical axis. That means it will not produce any sway. So sway is zero for this given problem. So this is, and we need to analyze the total frame by using non-sway analysis. We have to approach non-sway analysis. Low reflex method of analysis we need to approach here. Okay. So in the first step of in a given problem. So before going to solve this problem, first we need to identify the given figure, understand the given figure. Yeah. So support we have two supports A and D and two joints B and C. B and C. Two joints are there B and C. And the moment of inertia, these are the two column members. AB and CD are the column members. BC is a B member. Moment of inertia of AB and DC is I. Moment of inertia of BC member is 2I. Moment of inertia of BC member is 2I. Okay. So AB member and DC member is not subjected to any type of loading. It is not at all. They are loading is zero on the AB and CD member. Coming to the BC member is a B member that is subjected to uniform distributed load. Okay. So this is the given figure. Right. So in the for the analysis of this frame, especially in particular non-sway frame of analysis, non-sway frame. First step, what we need to do is we have to calculate the fixed moment. So we know very well about fixed moment. So fixed moment developed due to external loading. External loading. If you see AB member and CD member, there is no external load. There is no load. External load is zero. Horizontal or vertical. There is horizontal load is zero. Horizontal load is not there. So fixed moment due to loading is zero. MFAB and MFAB, MFBA, MFCD and MFDC are zero. Directly we can substitute they are zero. So coming to BC member, so BC member is subjected to uniform distributed load. BC member is subjected to uniform distributed load. For uniform distributed load, fixed moment can be calculated. MFBC will be equal to minus WL square by 12 and MFCB will be equal to plus WL square by 2L. Okay, we know this well-known formula for that. So frequently used formula. If uniform distributed load is there, the fixed moment MFBC will be equal to minus WL square by 12. MFCB is equal to WL square by 2L. So right here, W is equal to 40 km per meter. L is equal to 6 meters. Substitute here, you're going to get MFBC is equal to minus 120 kilometer meter. And MFBC is equal to minus 120 kilometer meter. And MFCB is equal to only change for MFBC and MFCD is only sign convention. So MFBC is producing anti-clockwise resistance. At B, anti-clockwise resistance will be there. At C, clockwise resistance will be there. Moment resistance is clockwise resistance. So that will be fast. Okay. So this is the first step in the problem. Next step, we need to develop slope deflection equations. So formation of slope deflection equations. So second step, formation of slope deflection equations. So we know this formula, slope deflection equation we need to write here. MAB is equal to MFAB plus 2 EI by L into 2 theta A plus theta B minus 3 delta B. So if you observe, AB member is this is frame is a non-sway frame. That means column members are not swaying, as well as B member is also sinking is not there. Sinking is not there. So that means delta we can substitute for all spans, like AB span, BC span, CD span. We can directly substitute delta is equal to 0. Here we observe unknowns. What are the unknowns we need to identify first? So here theta A is 0 and delta is also 0. Theta D is 0. Why? Because the fixed support. Theta B is unknown that we need to calculate first, and theta C is also unknown. So these two we need to calculate for. After calculation of these two, we can able to calculate the final moments. You know these values, we can able to calculate the final moments. So right, for that we need to develop these slope deflection equations for the. We have three spans. AB, BC, and CD. We can able to develop 6 slope deflection equations. We can form 6 slope deflection equations. Okay. First one is MAB. First one MAB. So MAB is equal to MFAB. So MFAB. For AB span, there is no external load. There is no external load. So that is MFAB is equal to 0. That means MFAB and MFBA will be equal to 0. So we can directly substitute this is 0. And 2 EI by L. L is equal to 4 meters. Substitute L is equal to 4 meters here. L is equal to 4. And theta A is also 0 because this fixed support. For fixed support, rotation is 0. Rotation of support is 0. And theta B is unknown. The delta is also 0. If you calculate it, you are going to get, if you solve this one, you will get 0.5 EI theta. You consider this is equation number 1. So now coming to MBA. So we know the formula for the MBA, calculation of MBA. MBA is equal to MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta Y. So here delta is 0, theta A is 0, L is equal to 4 meters, MFBA is also 0, substitute it. You will finally get this equation, that is equation. EI theta B values, that is equation number 2. Similarly for BC member and C member, BC member and CD member, if you write the slope deflection equation, so this should become equation number 3 and this is equation number 4 and this is 5. And this is 6. The only thing you need to substitute theta A 0, theta B 0, and MFAB, theta D 0, theta A 0, theta D 0, MFAB and MFBA is 0, MFCD 0, MFDC 0, and L is equal to 4 meter for AB span and CD span, L is equal to 6 meter for BC span. You substitute it and calculate, you just solve it. You're going to get 6 equations. You name those equations 1, 2, 3, 4, 5, 6 like this. AB is equal to 1, equation number 1 for AB, BA 2, like that you name for all the moments. So after formation of slope deflection equations, we need to write this joint equilibrium equations. We need to write the joint equilibrium equations. Okay, if you see, given figure is a frame, we have two joints. This is A and this is B and this is C and this is D. These are the A and D are the supports. B and C are the joints. You write the joint equilibrium equation. Summation of moments at joint B equal to 0. And next one is summation of moment at joint C will be equal to 0 because they are joints. Joints. Okay. What is my summation of moments at B equal to 0? Means whatever the moments available at B, if you add the moments at B equal to 0, that will summation of moments at B equal to 0. What are the moments are there for at B? At joint B, two members are meeting, BA member as well as BC member. At B, two members are meeting, BA member and BC member. That means moment in BA member plus moment in BC member equal to 0. Only two members are there, so two moments will going to develop at the joint B. So MBA plus MBC equal to 0. So we are calculated MBA and MBC in step 2. So MBA this one, MBC this one. Just add these two, 2 and 3 you add and equate it to 0. You add 2 and 3 and equate it to 0. Okay. If you add and equate to 0, you're going to develop another equation. Let us say this is equation number 7. Okay. This is equation number 7. Let us say. Now, another joint equilibrium equation is there. Summation of moment C equal to 0. If you do summation of moment joint C equal to 0, that means let us see two members are meeting. CB member and a CD member. So MCB plus MCD equal to 0. We are already calculated MCB and MCD in equation step 2. Add it and solve it. You are going to get another equation, that is equation number 8. From 7 and 8, the unknowns is theta B and theta C. Theta B and theta C. This is theta C. Theta B and theta C. Okay. Now what we have to do is from 7 and 8 solve for theta B and theta C. This is something like x plus ax plus by is equal to some a1x plus b1y plus is equal to c1. a2x plus b2y is equal to c2. Just substitute in the calculator a1, b1, a2, b2, c1, c2 value. You are going to get a xy value. X is nothing but theta b, y is nothing but theta c. Ei theta b, y is nothing but ei theta c. So these values you are going to get. The same values, whatever you are getting ei theta b and ei theta c, you directly substitute. You directly substitute. You are going to get that ei theta b is equal to 72, ei theta c is equal to minus 72. You directly substitute ei theta b and ei theta c in the step 2, MAB, MBA, we have now. So substitute ei theta b, ei theta c values in MAB, MBA, MBC, MCD, MDC, MD. All. You are going to get the final end moment. So after calculation of this final end moments, we need to draw the free body diagram. We need to draw the bending moment diagram. Okay. So at A, MAB is equal to 36 kilometer meter we are getting. MAB. MBA is equal to 72. MBC is equal to minus 72. Okay. MCB is equal to plus 72. Okay. Here we have plus 36, 72. Okay. This is minus 72. MCD is equal to minus 72. Okay. First of all, what we need to do is, for AB member and a CD member, there is no external load. External load less than 20. Okay. Here we need to represent the positive side. That is, this is 36. We have to represent like this. 36 ordinate we need to represent. Here 72 ordinate we have to represent here. Join both. Similarly for this column also. 46. Here 72. That is MAB is equal to 36 kilonewton and MBA is equal to 72 kilonewton. So this is negative and this is positive. Just join this. This is negative and this is positive. Join this. Okay. Now, so this is a continuous and there is a negative moment will be there. Continuous end దగ్గర మనకు negative moment ఉందని తెలుసు. Okay. So this is 72 and this here is also 72 is there. Join both. So this is this variation of bending moment diagram represents the hogging bending moment diagram. This is the hogging bending moment diagram. So now coming to the sagging bending moment diagram is due to applied load. So if you know, this is the uniform distributed load is acting 40 kN per meter. To calculate the maximum bending moment ordinate, and it is possible at the center, that is WL square by 8. If you solve WL square by 8, you'll going to get 180. W is equal to W is equal to 40, L is equal to 6. You're going to get 180. So maximum ordinaries are possible at the center. So variation of uniform distributed load ki bending moment variation is parabolic variation. So you draw like this. The variation is parabolic variation. The maximum ordinate is here we are getting 180 kN meter. So simply I'll write here. So this is the frame. I'll write. I'll write here then. User it. Here we have 36. Here is also 36. Here we have 72. Here is also 72. Just join these two. Just join these two. After that, here we have negative 172. This fixed that is a sagging bending moment. Here is also 72. Just join these two. Join these two. So this is the variation of sagging bending moment diagram. Now we need to draw the sagging bending moment. Sagging bending moment is due to applied load. So applied load variation is load entered uniform distributed load. For uniform distributed load, bending moment variation is parabolic variation. Maximum ordinate can be calculated as W square by 8 formula. So here maximum ordinate is W square 180. Locate 180 ordinate and join these 2 points by parabola. Join these 2 points by parabola. So this is the variation of parabolic variation. So this is the bending moment diagram variation. Let us say if this is subjected to a horizontal load on the then this will become this like this. The variation of bending moment is something like this. If it is hinged is there, let us say this is not fixed, hinged on the here the bending moment is 0. So something like this it will go like this. Okay. All right. Thank you one and all.